Hello everyone, this is Arun from myself Bhopal. We'll just shortly start the session in about like say 5 minutes. We're just waiting for a few more to log in. Thank you. Hello everyone, this is Arun from ISA Bhopal. I'm just waiting for the camera to turn. So for those of you who have joined online, thanks for taking time and joining the first lecture in the lecture series, Science and Local. Just to give in context, we are right now in ISA Bhopal auditorium, and we are doing it in a kind of a hybrid mode. And what you're seeing right now is the participants sitting in the auditorium. So I welcome the participants as well here. Okay, slowly the camera is coming. Probably then you will be able to see. Yeah, here I am. Sorry, I'm wearing the mask since we are following the COVID precautions here. So I invite everyone, and so I call Antara Chatterjee, Director of Humanities and Social Science Department at ISA Bhopal, to start to say a few words about the lecture series and start the lecture series. Yeah.
Hello, everyone. Thank you, Arun. Very good evening to everyone here, and a very warm welcome on behalf of the Department of Humanities and Social Sciences in ISA Bhopal. I welcome all of you here who are present in the auditorium, and of course, all of you who have joined us online. Thank you for joining us. So I would also like to welcome Professor Arun Bala, who is our speaker for this evening. Welcome, Arun, and thanks so much. Right, no problem.
It seems the audio is not working. Not audible.
Maybe we type, but we're just trying to figure out. Am I audible now? Yes. Okay. So I am told that I am audible now. Okay. One of the comments says that I'm audible to some people and not to everyone.
I think
Is it audible now?
it's saying it's not clear.
Okay, so I'm told that I'm audible, so I'll continue and I'll just repeat what I said in case I was not audible before. So, very good evening and a warm welcome to everyone who have joined us online and who are here in the auditorium. Very warm welcome to Professor Arun Bala, who is the speaker for this evening, and to Dr. Aditya Sharma, who is our colleague from the physics department at ISA Bhopal, who is the respondent for this session. Thank you, Aditya. And this is the first lecture in a series that is entitled Science and the Local. And my colleague Arun has taken the initiative of organizing this, so thanks a lot, Arun. And the idea behind this lecture series is to deliberate on the interactions between science, its practice, and the local, and contrary to certain assumptions about modern science as being universal, this lecture series aims to explore some of the intersections between science and its practice and the experience, the unique experience of the local, which shapes and determines the practice of science and its knowledge production. So with that, I think I will hand over to the speaker. So our director, Professor Shiva Umapati, was supposed to be here for the inauguration. Unfortunately, he couldn't make it. So I think I will welcome everybody once more on behalf of the department, and thanks and welcome Arun. And I think I will hand over to Arun now to introduce the speaker and the respondent. And we look forward to a very interesting and integrating lecture series. This is, as I mentioned, this is the first one, and we have three more scheduled in the coming weeks. Lectures by Professors Madhulika Banerjee, Morton McCord, and Sundar Sarupai. So with that, I will hand over once more to Varun to take it forward. Thank you.
Thank you, Arun. And for those who are present here physically and for those who have joined us online, kindly excuse for this technical glitches. I mean, we're just trying something out new here because, like, some of us were really tired of joining all the lectures online. We thought we have to slowly phase out and try this hybrid mode. And yeah, being adventurous comes at a cost. And sorry for this. Probably we'll work it out for the next time. And yeah, as Antara said, this is the first lecture in the series that we are planning to host here, titled Science and the Local. The idea is to see how science practice is very much informed, made, enabled, and created by the local configurations. And as very much to the spirit of this exploration, we felt that, like, apart from social sciences, philosophy, history, and various other humanity disciplines engaging with science, it is also important to bring the practitioner's viewpoint. And that was the rationale behind including the respondent from the science community. And so let me just briefly introduce the speaker and the respondent for today's talk. Arun Bala is a physicist and philosopher of science. He is the author of the Dialogue of Civilizations in Birth of Modern Science, and another book titled Complementarity Beyond Physics, Niels Bohr's Parallels. He is also the editor of a volume, Asia, Europe, and the Emergence of Modern Science and the Bright Dark Ages, Comparative and Connective Perspectives. He has held teaching and visiting positions at the National University of Singapore, as well as the University of Toronto, Western University, and Dalhousie University, Canada. So thanks, Arun, for agreeing for speaking in this lecture series. I also invite Aditya Sharma, who is an assistant professor in the physics department at IISER Bhopal. He works in the broad field of condensed matter physics. His approach to research has been an amalgamation of analytical and numerical methods and physical intuition, while covering a range of topics at the interface of statistical physics and many-body quantum physics. In recent times, his primary focus has been on uncovering a fresh quantum information perspective to many condensed matter phenomena. Thanks, Aditya, for being here. The format that we'll be following is Bala will speak for around 40 to 45 minutes. After that, I invite Aditya to respond for 5 minutes. And after that, we can open the discussion to the audience. So Bala, are you able to unmute yourself and talk?
Okay, can you see me, Varun?
Yes, I can see and hear you as well.
Okay, that's good.
I hope the rest of the participants who have joined us online are also able to clearly hear Arun. So, yes, so yeah, we have some feedback saying that yes. Arun, can you start your presentation?
Okay, thank you, Varun. I'd like to first begin by thanking the Indian Institute of Science Education and Research for giving me this opportunity to discuss issues that are quite close to my heart. And in particular, I would also like to thank Dr. Antara Chatterjee, the head of the Humanity and Social Science Division in the Institute. And most of all, Dr. Varun Bata, who actually wrote to me some time back about this series and invited me to participate in it. And it sounded quite exciting, and I willingly agreed. So what I'm doing here is trying to share some of the ideas that have come out of actually an early book of mine that I will refer to in the course of the talk, and their further developments. And I must begin by saying that this is very much an exploratory talk. I have not actually, worked out a paper or a coherent account about the kind of conclusions I will be reaching. But nevertheless, they have been very much in my mind, and my talk will be about that. Now, the title of my talk is Asian Geocentric and Modern Heliocentric Astronomical Traditions, Theoretical and Methodological Connections. Now, by Asian, I am of course referring to actually three major traditions in Asia: the Indian, the Chinese, and the Arabic. The Arabic is sometimes known as the Islamic tradition, but I think it's more accurate to describe it as Arabic because the people who contributed to that tradition were Christians, Jews, as well as Muslims, and came from a wide diversity of cultures. Now, in order to begin the talk and lead into the discussion, I would like to, well, let me see if this can move. Okay, I would like to give an introduction to the kind of approaches that I'm making. Now, as I have already said, that there were three pre-modern Asian scientific traditions: the Indian, the Arabic, and Chinese. Some might want to say, actually, we shouldn't call them just Asian, because the Arabic tradition also developed in North Africa and to some extent in Europe, in Iberia, when the Muslims were ruling in those territories. But I am sticking to the notion of Asian scientific traditions because most of the traditions I will be looking at developed within the Asian context, either in South Asia or in East Asia or in West Asia, in the region of the Middle East. Now, there's been a lot of literature over the last 3 decades that have begun to look at modern science not in terms of how it just simply developed from within Europe, but also how it came about because of the circulation of knowledge across the whole Eurasian region. And this has been read into a lot of disciplines. For example, the circulation of mathematical knowledge across the Eurasian region, the circulation of chemical knowledge in the form of alchemical traditions, this biological knowledge, medical knowledge, and even geographical knowledge as empires, went back and forth across the region and needed knowledge about the territories they control. And all of this kind of knowledge that circulated actually began the circulation a very long time ago. We know of Babylonian and Mesopotamian knowledge that circulated into the Greek heritage, and also that circulated into India to some extent, and even to some extent into China. And also Indian mathematics circulated into the Islamic world and also into the European world. And surprisingly, though it's not been studied to the same extent, even to Southeast Asia, where I am located now in Singapore. So this kind of circulation involved different kinds of knowledge. It could be empirical knowledge, about matters of fact. It could be theoretical ideas or mathematical techniques, and even methodological orientations. Now, I won't go into that because my specific interest in this talk is with astronomical traditions. So what I want to look at is this Eurasian dialogue in science, that or Eurasian circulations of knowledge in the making of modern science, particularly in the area of astronomy. And the three traditions, as I mentioned, are those that came from, India, China, and the region of the Middle East, the Arabic traditions. The reason I put this book up is because this is a book that I wrote in 2006, seems like a long time ago, where I actually looked at the Copernican revolution and the way in which Islamic, or what I prefer to call Arabic, Chinese, and Indian traditions also contributed to its making. And what I want to do now is to look at the three traditions that came together. The really important traditions were the ones that culminated. These were the culminations of the astronomical traditions. That is, they reached their highest degree of precision, sophistication, and accuracy. In India, it culminated, I would say, before the pre-modern era with what has come to be known as the Kerala School of Mathematics. That is the Indian Kerala School developed of course, in South India, in the region of Kerala. And then you have the Maraga School of Astronomy in the Islamic tradition, which developed somewhere in the region of Iran. And in China, the infinite empty space theories. I am sort of putting this forward, but I will give a more detailed account of these later as the talk proceeds. Now, but first I would like, since most people may not be aware of the Asian astronomical traditions, because they are still kind of marginal or have a marginal status in the disciplines like the history and philosophy and sociology of science, which generally tend to focus on the growth and development of scientific knowledge within Europe, whether it be old Europe in Greece or the young Europe, if you can call it that, which emerged around the time of the Renaissance and continues to this day. Now, there is a book written by an Indian author, George Georges Joseph, entitled, it's The Passage to Infinity. It discusses the growth and development of Kerala mathematics, as he calls it, because it developed in Kerala, but it is really medieval Indian mathematics. And through a sequence, of mathematical astronomers whom I have listed there. The important names in this tradition are Madhava or Madhavan, and Nilakanta, and Jayastadeva, these three whom I will be focusing on. Madhava was the pioneer who began the tradition. And it was a tradition that dealt with the summing of numbers, but not just a finite sequence of numbers, but infinite series. They developed an account of numbers, for instance, the infinite expansion of tangent as a series, or the sine series, or the cosine series. And this was something that was done in order to deal with astronomical problems. The other school that I want to look at also, which developed around the same time, was in the Arabic world, and it came about with the founding of the Maraga Observatory under the Mongol ruler Hulagu Khan. And Hulagu was a descendant of the Genghis Khan down a couple of generations. And even though the Mongols are often seen as uncouth or barbarians, they actually, were great patrons of knowledge and learning as well. And Hulagu actually built an observatory there under the directorship of a great mathematical astronomer, Nasir al-Din al-Tusi. And this astronomical tradition took astronomy that the Arabic scientists had inherited from the Greeks and advanced it a lot further by developing various mathematical techniques that led to a theory that in some senses was an improvement on the ancient Ptolemaic theory. And one might even think that it was a considerable revision of it, though it was still within the Earth-centered perspective of ancient Greek astronomy. And the names there of these astronomers like Nasir al-Din al-Tusi, Muayyad al-Din al-Urdi, Ibn al-Shatir, these are names, of people that I will be talking about a little later. The third school is the Chinese. Yes, and the astronomy, and Chinese astronomy did not focus on planets like the Indian or Greek traditions, but they focused on the constellations of the stars, on mapping them out. And they were also astronomers who actually observed the heavens by building mechanical celestial spheres that kind of followed the path of the heavens, on which they map the constellations the way they map countries on the globe of the Earth. Now, I think I might, just say something about what happened is that in modern astronomy, a lot of ideas from these various traditions came together. They could be ideas about, data on planets, about eclipses of the sun and the moon, comets, sunspots. There were also theoretical ideas from the different astronomical traditions that also went into the making of modern astronomy, as well as mathematical ideas and cosmological ideas like the infinity of space, the voidness of space, and so on, which was actually emphasized in Chinese astronomy. Now, what I want to do, is I don't want to go into the details of the contributions of these various traditions, but what I want to say is that accounts like these have become, very available today. And when I did my book 15 years ago, it was about these different confluences of empirical, theoretical, mathematical ideas that came from different cultures and civilizations and contributed to modern science. Now that these sort of views have become more prevalent, there has been another way of saying that the Asian traditions, even if they did contribute significant conceptual ideas and theoretical ideas, nevertheless, did not really make the most significant contribution to modern science, which is, the way that knowledge is constructed in the modern world, scientific knowledge, in contrast to the way it was constructed in pre-modern times. And that is, there is a kind of the philosophy, the epistemology, and the methodology of modern science is very different from that of the earlier traditions. And these were not derived from ideas produced from the Asian traditions, but they somehow emerge sui generis within Europe itself, rooted in its own earlier Greek tradition, or something that emerged within modern Europe. And this is actually argued in a book by a historian, Floris Cohen, is a Dutch historian. And this book, The Rise of Modern Science Explained, a comparative history, was published by, I think, Cambridge University about 6 years ago or around that time. And it's a shorter version of another book that was published earlier by Amsterdam University Press a few years earlier. Now, Cohen's argument is that what is important about science is not the theories or the empirical data, or or simply the cosmological views, but the way we construct knowledge, the modes of nature knowledge. And he thinks that modern science actually can be characterized as the coming together of three different modes of nature knowledge. What he calls mathematical realism, that is the idea that mathematical relations must actually reflect the real world in some sense. The other is the notion of kinetic corpuscularism, and the third, fact-finding experimentalism. Now, let me explain what he means by this. In Greek astronomy and earlier, the tradition was that one constructs mathematical models, as Ptolemy did, in order to make predictions about how the heavenly bodies move. It doesn't matter whether the heavenly bodies actually follow these regularities that the mathematics gives you. That is, the mathematics is just as an instrument, a tool to make predictions, but it is not embodied in the world of astronomy itself. Now, the other notion, and this was something that was accepted by Ptolemy, the Greek astronomer. Now, kinetic corpuscularism is the idea that the world is made up, that the world is made up of atoms is a very ancient idea. And the ancients explained the properties of material objects largely by looking at the shapes, the sizes, and other properties of the atoms. But the modern atomism is not concerned with the actual properties. Of course, that's not true now. But early modern atomism was concerned more with the way atoms move. That is, that the explanations of events were in terms of the momenta of atoms or the energy carried by atoms and so on. So that you moved from a corpuscularism, a physical corpuscularism, to a kind of a corpuscularism of motion or a kinetic corpuscularism. And the third idea is experimentation, that we discover facts by doing experiments. This was something Cohen thinks that uniquely emerged in modern Europe. So even if Asian traditions did contribute ideas and concepts to modern science, they did not play an important role in the modes of nature knowledge that went into the making of modern science. This is his argument. And I want to say that this is actually not true. That we can show that not only did, in the case of astronomy, not only did ideas of astronomical ideas, concepts shape the tradition that developed, but Asian traditions also contributed to the kinds of methodological approaches or modes of nature knowledge that Cohen is talking about. Now, so let me go through this to illustrate what I've said. See, in the Arabic Maragha School of Astronomy, the Ibn al-Haytham, who lived around this period 965 to 1040, he criticized the astronomical theory that the Arabs had inherited from the Greeks, because he said they should not merely save the phenomena. They should not just do the mathematical instruments, but they should also offer a physically plausible mathematical realist model of the heavens. Now, the reason for this was that in Ptolemaic astronomy, in order to account for the motion of the planets, Ptolemy had to say like a planet like Jupiter, that it moved in a circle. It actually moved in an epicycle, that is a circle on a circle, but the epicycle center was not centered on the Earth, but was centered somewhere else. And it needed an equine point, and so it moved around an eccentric, and the equine point was something in space. Now, this idea of the equine is an imaginary point in space that controls the orbits of the planets. And this was something that he had to use because he couldn't develop a realist model of planetary motion. Now, Al-Haytham objected to that. He said, what we need is a model of planetary motion that would not need something like the equine, an imaginary point in space around which motion gets defined. And the Arabs then set out to discover ways of getting around the problem. I won't go into this, but they developed two mathematical theorems, the Tusi couple and what is known as the Urdi lemma, in order to solve the problem. And they managed to get to a model with Ibn al-Shatir that by using the Urdi lemma and the Tusi couple was able to eliminate the equine. And here's a model of, you have a model of Mercury there, that doesn't have the equine. All the orbits are centered around physical bodies. Now, what is very interesting is that the Maragha school model later was identical, at least mathematically, to the model developed by Nicholas Copernicus when he formulated his heliocentric theory in the 16th century. Now, the question is, did the Malaga school influence Copernicus? But even if it didn't, it is quite striking that this Arabic Malaga school arrived at theorems that were also important for the emergence of modern astronomy or heliocentric astronomy. Now, the Indians actually had a very different astronomical model from the Arabs or the Greeks. They did not think of the planets and the sun and the moon as revolving around the Earth. Their model, strangely, assumed very early on that the planets we see, like Mercury, Venus, Mars, Jupiter, and Saturn, revolved around the sun, but that the sun itself actually revolved around the Earth, more or less. This is the kind of model they assumed. And you can see the Indian astronomical conception in the Indian temple Navagrahas, for instance, where you have the sun at the center with the planets going around it. And of course, there are these two fictional planets, Rahu and Ketu, that are designed to account for eclipses of the sun and the moon. Now, what is interesting is that in order to deal with this planetary motion, to account for that planetary motion, the Indians also discovered very powerful mathematical techniques to deal with the kind of motion. What they had to do was to calculate the motion around the sun of the planets, and then recompute it with the sun moving around the Earth in order to get the actual positions of the planets. And the method they used was very much not the geometrical method of the Arabs or the Greeks, but algebraic techniques. And as a result of this, they discovered important theorems that anticipated, in some sense, infinite series expansions we have today, and even notions of the calculus. For instance, the inverse tangent series is now attributed to James Gregory, but and the pi, the series attributed to William Leibniz, and the sine and cosine series to Isaac Newton are known to have been discovered by the Kerala astronomers and to be used by someone like Nilakantha to deal with planetary problems. And Jayastadeva, who is a follower of Nilakantha or lived about the same time, also gives an account of it in his book, the Yuktibhasa, which also gives proofs for some of the Kerala school discoveries. Now, and these discoveries also were important for modern science, but they can be seen as having been anticipated in the Indian Kerala school. And we know that someone like Vasco da Gama actually came to India at the very region of the Kerala school in 1498, which was before Nilakantha published his Tantra Sangraha or Jayastadeva, and way before the Yuktibhasa was published. Now the Chinese, if we now turn to the Chinese, their conception of the heavens was not geocentric as with the Arabs, nor geoheliocentric as with the Indians, but they saw the heavenly bodies as moving around the pole star. Now, this is a time-lapse photography of how the stars move. And we know they move like this around the pole star because of the rotation of the Earth. The Chinese did not know that, but they did observe the rotation of the stars around the pole star. And here is a Tang Dynasty map that shows this kind of rotation. Now, in this rotation enabled them to actually build models, physical models, that rotated with the heavens to keep track of the heavens. But the mathematics for building these models, we can call this the approach they made a kind of a mechanical modeling, the methodology of mechanical modeling, but it also needed mathematics. And since the Chinese mathematics was not as well developed, and this could be a controversial issue, as the traditions either in the Arabic or the Indian world, Chinese astronomers actually drew on Indian astronomers during the Tang Dynasty when Buddhism was quite dominant, and on Muslim astronomers during the, or Arabic astronomers during the Yuan Dynasty, when the Mongols had conquered territories from China and across to the Middle East. And during the Ming Dynasty, when Europeans, especially Portuguese astronomer missionaries, traveled to China, such as Matteo Ricci. Now one can ask, why is this so important? If you think about it, when the heliocentric theory was proposed by Copernicus, that is the theory that the Earth rotates on its axis and revolves around the sun, in a certain way, it brought the other traditions together. The rotation of the Earth is actually what causes the heavenly bodies, as the Chinese saw them, the stars, to rotate around the pole star. They rotate anti-clockwise around the pole star because the Earth is making a clockwise rotation on its axis. Similarly, when Copernicus also proposed that the Earth not only revolves on its axis, but also makes annual rotations around the sun with the other planets, it kind of aligned with the Indian astronomical traditions because the Indians had already assumed that the other planets like Mercury, Venus, Mars, Jupiter, and Saturn did revolve around the sun, except that they also further assumed that the sun itself then revolved around the Earth, which is what made their astronomical model a geo-heliocentric model. But this meant that the techniques and the mathematical techniques used by Indian astronomers to deal with planetary motions around the sun could be transposed into the modern Copernican context. And Copernicus himself, as we have said earlier, developed certain techniques that were adopted by the Malaga School astronomy in order to deal with his own astronomical problems. Now, that is, he used the Urdi lemma and he used the Tusi couples, that the Malaga School had discovered in order to solve problems within his heliocentric theory. Now, this led a historian like E.S. Kennedy, for instance, he said, that the solar, lunar, and planetary models of Ibn al-Shatir are mathematically identical to those proposed by Copernicus. Another two historians in their study mathematical astronomy in Copernicus's work, De Revolutionibus, they write that Copernicus can be looked upon as, if not the last, surely as the most noted follower of the Maraga school. And this is what led someone like George Saliba, who wrote about the Maraga school and who studied the Maraga school astronomy from a historical point of view, to say that we have strong circumstantial evidence that the Maraga mathematical approaches actually influenced Copernicus. So what we can say is that there are these conceptual connections with the Maraga school and Copernican astronomy. Now, similarly, the Kerala school also can be seen to have influenced modern astronomy. Partly, as I've already mentioned, the Portuguese arrived in Kerala in 1498, and leading mathematical astronomers like Nilakanta published his work 2 years after Vasco da Gama arrived, precisely in the region where he was working. And the Yuktibasa was also published there, 50 years or more than 50 years after the arrival of the Portuguese in Calicut, where Jestadeva himself was writing. So again, there is kind of evidence that Indian conceptual connections have to be taken seriously in relation to the growth of modern astronomy. Now, since I have been assigned about 40 minutes, I think, I might have to go a little bit faster. You can find the same thing in the case of Chinese astronomy. That when the Europeans arrived in China, one of the leading models was the infinite empty space model, which said that the heavens were empty and void of substance. This was something that the Europeans found very hard to believe, because according to Aristotle, there could not be a void. It's impossible for a void to exist. Now, they also believed in a lot of other things about heavenly bodies being sort of condensed out of vapor and so on, that I needn't go into in detail. But many of these ideas were so strange that the astronomer Matteo Ricci wrote back to Europe in 1595 that when he compared Chinese astronomical beliefs or cosmological beliefs with his own, they seemed to him to be quite absurd. The Chinese believe, for instance, there is only one sky, but the Europeans believed there are 10 skies, because they believed all the planets were attached to solid spheres that rotated around the Earth. That the Chinese believe space is a void, but European astronomers did not. That the Chinese believed that the stars move in the emptiness of space, but European astronomers believed they were fixed to a crystalline stellar sphere. Now, there were other things that the European astronomers thought did not exist, namely phenomena like comets or exploding supernovas or sunspots. They did not notice sunspots because they believed in an unchanging heavens. Objects like comets, when seen in the heavens, were thought of by European astronomers or as actually emanations from the Earth, having nothing to do with the space beyond the moon. So, and the other thing that Matteo Ricci must have been impressed by is the building of mechanical models of the universe that the Chinese constructed which rotated with the heavens. And in order to do that, they had to use what we now call the equatorial mounting. But this mounting was something that the Europeans did not use, but which they later adopted once they came to believe that the Earth was actually spinning on its axis. So it was good to have astronomical instruments or celestial spheres rotate with the Earth so as to keep track of the heavenly bodies. Now, so all of these are different kinds of ideas that were there in the other astronomical traditions. And there is some evidence that they actually came to shape a modern astronomy. But now we see that there is another way to get around the problem of the specialness of modern science and its insulation from the Asian traditions, which is what Floris Cohen had suggested, that there were these three modes of nature knowledge, which he attributes to scientists like Kepler, mathematical realism, René Descartes, kinetic corpuscularism, and Bacon as the one who proposed the experimental method, fact-finding experimentalism. Now, the thing is, I'm not sure that I will be able to go through the whole arguments here, but what we can show is that what he thinks of as mathematical realism that emerged in Europe was also influenced by the mathematical realism of Arabic astronomical traditions. Because one of the criticisms of Ptolemy's astronomy was that it didn't provide a physically real mathematical account of the world. And this was why we found within Arabic astronomy the need to develop mathematical theorems that were able to resolve this problem. And this was what finally the Malaga school succeeded with the Ibn al-Shatir mathematical model. Now, it's the same thing with what is called kinetic corpuscularism. Now we think that modern atomism is somewhat a successor of the ancient Greek tradition, especially if we are within a mainstream history of science. But the historian Alexander Koyra, for instance, said that Greek atomism was never successful, to the same extent as modern atomism, because it was sensual. It was not able to develop a mathematical theory to deal with atomic phenomena. And one argument that could be made is that this cannot be done within the number system, say, of the Romans or what the Greeks had. That you needed the notion, because modern atomism requires the notion that the whole can be treated as the sum of its parts. And this is very crucial for the development of 17th century physics. Many of the fundamental concepts of physics like mass, momentum, volume, force, distance moved, time intervals, in all of these cases, the whole time interval is the sum of its parts. The whole spatial distance is the sum of its parts. A force is the sum of the separate forces. Of course, you have to do some kind of vector addition there. Volume, the volume of an object is the sum of the volumes of its parts, and so on. Now, the reason that we can now work with a kind of mathematics that is able to deal with parts and sum them into wholes is because of the Indian number system. The decimal place value system is 0. which provides a powerful instrument for for what we can call an atomic mode of analysis. This is not, atomism in the physical sense alone. It's not, we are not just simply talking about physical atoms. We are talking about, a mode of analysis that involves dividing something into parts and then adding these parts together to get the value of the whole. And we do that with many things. And this is only possible because of the number system we have today that is a heritage from the Indian tradition. And in the Indian astronomical tradition with the passage to infinity, we even have the notion of summing things in an infinite series to get some kind of a finite value. So if we can call it mathematical atomism, then this is something that is different from the narrower physical or material atomism of Greek thought. So that, and when we think of the differential or integral calculus, it's also a natural extension of the mathematical atomism embodied in the Indian number system, because we compute areas, volumes, etc., by dividing them into very tiny infinitesimal parts and summing them up together. Now, and we could say that therefore, what Cohen calls kinetic corpuscularism is something that would not have been possible, as an approach in modern science if it were not for this mathematical system inherited from the Indian tradition. And finally, I don't want to, since I'm running short of time, I don't want to go into the details about the Chinese method, which is very much a kind of a experimental approach to things that led them to make discoveries like the compass, printing, gunpowder. It's a trial and error experimental method where they make models and improve on models in order to lead to make new inventions and new extensions of knowledge. And this experimental method that we think of as being first clearly formulated by Francis Bacon can be seen as inspired by Chinese discoveries, which Bacon himself acknowledges. He said that, that these, though he did not know where they came from, like gunpowder, printing, and compass. Now, what I would like to do now is to say that when we look at the Asian traditions, we can trace not only conceptual connections, but also methodological connections that went into the making of modern science. Then why has the this leads to a certain question. Why has mainstream scholarship in the history, philosophy, and sociology of science largely ignored these wider Asian connections, Eurasian connections? And I think the main reason is that over the last few decades, we have largely focused only on what can be called the transmission problems. How do we establish, that certain ideas were transmitted, into Europe in the modern era, that came from outside, and was it real transmission or was there independent discovery? And this debate has gone on decade after decade, and it has actually precluded addressing the wider implications of such transmissions. Now, you can think of, and I'll just quickly run through, you can think of the traditions like the Malaga School of Astronomy, the Kerala School of Astronomy, the Chinese 1 Yi traditions as not simply theories. They were not just conceptual frameworks or cosmological ideas, but they also carried methodological orientations. In a way, they are like what we could call research paradigms, which carry both ideas, empirical data, as well as methodological orientations. But what is interesting, if we take this account I've given in astronomy seriously, is that a multiplicity of research paradigms from different cultures somehow came together and contributed to modern science. Now, if that's the case, then the issue of connecting science and the local, which is what this series of talks is about, has some implications that we might want to consider. For instance, should we now write histories of science that are comparative? That is, should we write a history of Chinese science, of Indian science, of Arabic science, of Western science, or European science, and then somehow compare them, their differences, but see them all as running in separate tunnels of their own? That is, write tunnel histories of different civilizational sciences. Or should we actually turn to writing connective histories? And if we do that, what does it imply for history writing? This is something that might be worth considering. Another implication of this is for philosophy of science. Most of our philosophies of science, like hypothetical deductive methods, or the method of conjectures and reputations of Popper, or the structure of paradigm revolutions associated with Kuhn, or Lakatos' scientific research programs, and so on, they have an agonistic orientation to the different conceptual frameworks that emerge. That is, one framework emerges and then is displaced completely by another, and then another succeeds a third, and so on. But what we have here in this pattern in astronomy is different astronomical traditions somehow coming together and coming to shape a new tradition that emerged in the modern era. So that we need a kind of a philosophy of science that has a kind of a dialogical methodology, if you want to call it that, that can accommodate these kind of confluences as well as competition at the same time. And finally, I think what I want to say is that this kind of approach also has implications for sociology of knowledge. We can't answer questions like, why did modern science develop, say, in Europe and not elsewhere, by looking at some essential characteristic within Europe, either its religion or geographical contours or some other parameter within the culture. Instead, we must ask, why did this dialogue of different cultures across the Eurasian region that continued over thousands of years suddenly lead to a change that appeared in Europe that led to modern science? What was the situation there relative to the others that made this difference? And these kind of questions, I think, have yet to be addressed seriously. And I would like to propose that if we take into account these confluences of different traditions that went into the making of another tradition, we would have to take them and deal with them in a serious fashion. Thank you.
Thank you, Bala, for this wonderful lecture. I invite now Aditya Sharma to respond to this talk from his perspective.
First of all, let me thank Professor Bala for this fascinating lecture. So there were lots of ideas and facts which were completely fresh and new for me. So one thing that sort of stands out. So I also thank Arun for giving me the opportunity to respond. Yeah, so one thing which stands out from this talk for me is, this how nonlinear so the development of scientific ideas are, right? So there are these different schools working with so much passion and drive in their own little box. So there is this local aspect to it in the sense of geographical locality, but also in terms of boxes of ideas, right? So for example, the Kerala School of Astronomy, so they had it, they thought that the sun was going around the earth, and so perhaps it would require quite a leap of imagination for them to let go of that one idea and to see the bigger picture. And on the other hand, you have this the European insistence that it's impossible for to accept a heliocentric model, and how do we know how the kind of revolution that had to take place before they could let go of that. Right. So, but I mean, within their local box, so there is so much activity, and then there comes a time when there is a maturing of all these ideas, and where there's a kind of blow which comes from outside, right? So, so what I would like to say here is that there is this organization of ignorance in some sense, right? So every school or every approach brings out a systematic organization of ignorance, and then there is this blow from outside which comes in, and so this systematic organization of ignorance leads to knowledge, right? So ultimately, that's what we all care about in some sense. That's the goal of science, is to take us from ignorance to knowledge, right? So, and then coming to this idea of local, right? So in the modern context, so the word local itself perhaps needs to be looked at afresh, right? So we have this, it's not just geographical locality involved, right? So we have boxes which are formed in a different way, right? So we have small groups which are working on a certain idea or in a certain direction, basically, right? So what are the dogmas that you have to work with? I mean, dogmas are important because if you set up dogmas and put them together in a constructive way, it gives somebody else the opportunity to destroy those dogmas, and then you get knowledge. So in that sense, dogmas are important. So I just want to end with an anecdote from my own experience, which is, so I used to be a postdoc in Brazil, and I was thinking about this problem, which is, it's called the Ising ferromagnet on a K tree, right? So, but for a couple of years, I was thinking about it and not really making progress. And then I moved on to a different postdoc, which was in Israel. And so then it appeared like I had many of these clues together, but they were not fitting together in some sense. So then I wrote to this professor there, Professor David Mukamal, and said, can I come and chat with you about this little problem? And then he said, okay, let's talk about it. And so then when I started describing this topic, he said, but this is a very old issue, and it has been sort of, I'm surprised that you're still thinking about it. So I had a fresh way of thinking about it and a new question. So he was not dismissive, but rather quite supportive that, or expressed happiness that there is something more interesting still to do in what was an apparently mature field. But in any case, so then I went ahead and described my whole problem, and so this whole issue or this whole exercise of describing your own attempts can sometimes just yield answer. So in half an hour at the end of this conversation, I had in fact sort of seen the picture, and on this bus journey back home from Weizmann University back to Tel Aviv University, I basically solved the problem. So, and then at the end of this journey, I wrote back to him saying that I have the answer. Would you like to be a co-author on this paper? He said, no, it's your work. And in fact, by the end of the week, I had the paper out as well, right? So what I'm saying is that there is this sense of organizing your ignorance in a sort of systematic way and repeated reorganization. And sometimes you get a blow from somewhere else, and that can lead to progress. Thank you.
Thanks, Aditya, for sharing your thoughts. Bala, do you want to quickly respond to some of the points, or shall we open it out to the discussion?
Well, I'd like to respond to one point.
Please go.
Especially, I think I like the idea that every approach brings a systematic organization of ignorance and leads to knowledge. And I think this is actually true even of the astronomical traditions I was talking about, the three Asian traditions. Each of them carried systematic knowledge, but they also carried systematic ignorance in other ways. And and somehow the coming together of them allowed modern science, I would say, to get a richer perspective precisely because of this confluence. But we can also think of modern science itself as another, maybe becoming another local tradition if other traditions develop outside it that begin to question it. Of course, we know that the second revolution in physics did actually do that with Einstein and quantum mechanics. And many of these new ideas, like in quantum mechanics, developed within local pockets, but they grew out and interacted with a lot of other ideas and reshaped science. So I think the interactions between the local and the way different local traditions come together to form more integrated traditions, which themselves then become local and go on to interact with other traditions, something that is worth looking at. It's like the Jain idea, that we have all multiple perspectives on things. And each perspective gives knowledge in some way, but also, clouds our knowledge in other ways. I think I like that kind of metaphor, if I call it that, that Aditya introduced. Yes.
Thanks, Bala, for sharing your thoughts. Now I call upon the participants to share their questions, points, start the discussion. So since we are doing it in the hybrid fashion, so probably I can take, from the people who have joined online, if you can kindly raise your hand, then I can keep assigning you. And in between also take the questions from the people who are present in the auditorium. So I see Vinita has raised her hand. Vinita, we'll just unmute you. Can you please ask your question?
Hi, can you hear me?
Yes, Vinita, go ahead.
So I have a quick question, given what we're discussing in terms of the locals and getting ideas from different region, which is very well presented by Professor Bala. My question is, do we have this kind of thought process anymore, given that now we're just one massive connected sort of science group, or is it even possible to have these kind of different ideas coming from different regions? Because, like what Aditya said, that, there were local pockets of ignorance, right? And sort of a systematic ignorance. Do we have that anymore now? Or is it even, or have we lost it because of the connectivity, which has its own advantages? But does that also mean that ideas are quite homogeneous now?
Should I be answering that question?
Yeah,
Arun?
what you prefer? If you prefer taking questions, then we can collect the questions, or if you want to answer.
Well, I'm happy to answer them one by one.
Yeah, then let's go with that. Yeah.
Okay. Whichever way you prefer, but I'll answer this question. I think it's a very interesting question that Vinita has presented. it is quite true that the different regions in the past, like China, India, and the Arabic world, and possibly Europe itself, developed in isolation from one another, and which is why, to some extent, we think of them as separate civilizations, even though they were not, and they were interacting with each other. But these interactions were not so intimate that it prevented very different astronomical traditions as well as medical traditions, and other kinds of traditions, religions, etc., from developing in different ways. Now, what about the modern world? Of course, we live in a world that is connected by the internet, but one of the interesting problems that has recently emerged is that the internet, instead of connecting us all together, some people argue it's actually dividing us, because what is happening is that different groups of people are actually choosing to go into different spaces, and work within those spaces so that we become more isolated from each other. And even the algorithms that present, the results of searches to us, try to predict what are our interests, and then, pre-select, what we see on the screen, so that we seem to somehow fall into a deeper and deeper hole of our own making. Now, if this happens, yes, even though we are much more intimately connected, via, in cyberspace, if we want to be, what is actually happening is we are also getting more and more isolated from each other. I mean, groups, at least as groups. Maybe not in the same geographical area, but maybe in different ideological spaces. And I don't know whether this would be fructifying or inhibiting for the growth of scientific knowledge. But it's a very good question, very interesting question.
It's quite of interesting. I'm a biologist, so I mean, we see sort of similar thought processes also in basic sciences, in botany or zoology, how we looked at evolution, how we looked at organisms. Sort of there were these very interesting schools of thoughts that at one point it was dominated by the European ideas, and others were lost, but of course recovered again. But now we see sort of this dominance of certain ideas only from a certain direction. And that diversity of thought, and maybe again, I have to look into what you just said, that ideas are still isolated. And I think that's something I may want to, I'll probably look into it. But the thing is, I guess the voices are so drowned because it's all connected. And so I think the ideas and thoughts also tend to sort of magnify themselves in the internet world, because everything is connected. You see one idea and everyone gets hung up on it until someone really says it's really wrong. And unless that voice comes from somewhere big, it's not heard anymore. So I think, yeah, it's kind of interesting to see how the history of science sort of affects the thought process in the air. Thanks a lot. Thank you.
Anyone from the audience here who have a question? Yes. Can I request you to kindly come to the file and for the people who are online, we have a question from the person here who's present. We'll take the question from there and then come back.
Thank you, Professor Bala, for a very nice talk. I particularly liked your idea about. Should I just remove this for a minute?
Yeah.
I particularly liked your idea of corpuscular realism. I forgot the exact word. Having to have a mathematical basis in Kerala School of Mathematics. However, I am somewhat unconvinced by the fact that meaning the fact that it is necessary for it meant that the Indian or Asian tradition had anything contributed in the actual corpuscular, kinetic corpuscularism or something, the word that you use, largely because the physical concept of a particle, in spite of being Kanad having been there and having already said about the world being made out of particles, was not appreciated in that kind of a physical way. So in some sense, Kanad's idea remained isolated even within India from the Kerala school, and they didn't get fructified or unified in India. And that's what something happened in Europe. So to that extent, that's a major development there.
Bala, you want to respond?
Okay. Yeah. Okay. I think, when I was suggesting that mathematical atomism, was made, I was not actually suggesting that mathematical atomism was made possible by the discoveries of the Kerala school in infinite series. What I was actually suggesting was that mathematical atomism was something that became possible only because of the number system that was discovered in India, where you could actually talk in terms of very indefinitely large numbers, and you could also talk of indefinitely small entities, of very small sizes, and this idea can be separated from the infinite series idea that the Kerala mathematicians discovered, which actually built on the Indian mathematical system, except that, when they came to numerical methods of computation, they made the passage to infinity. That was what the book that, by George Gilbert Joseph was about. But one can make a case then to say that without that mathematics, if we had to depend on, say, Roman numerals or the Greek numbering system, it would have been very difficult to develop, say, Newton's theory of gravity, for instance, and apply it to planetary motions and apply it to other phenomena like projectile motions and so on. And if I wouldn't want to say it's impossible, because, I'm not, probably someone with sufficient genius could have done it, but it would have been very difficult to do that. So that the number system is as important for modern science, not only because it provided us with a number system, but it also provided us with the idea of mathematical atomism, which is something quite different from physical atomism that could be applied not just to physical entities, but also to things like volumes, forces, spatial intervals, time, and so on. Now, this is something I'm not sure whether you would agree with me, but this is something I find difficult to see as possible with the kind of number systems that were there earlier. That's what I meant. So I'm not giving the credit to the Kerala mathematics. The Kerala mathematics, of course, took the atomic analysis to infinitesimal, smaller and smaller numbers, okay, in order to reach, sort of notions that are very close to modern calculus and modern, integral and differential processes. To deal with particularly astronomical phenomena, you have to remember they use these methods to deal with astronomical calculation, they didn't extend it to all domains of the sciences as, was done in the modern era. I'm not sure if I'm making myself clear, but, there are two things I wish to separate. The number system that made mathematical atomism possible, and the passage to infinity that made certain other more sophisticated computing procedures that led to the calculus possible. But both depend on the number system.
Thank you, Bala. Any questions? If not, I have a question to ask Bala. So just going from where Vinita pointed out, like how can we start understanding what you're talking for the modern contemporary science, vis-a-vis the particular slide that we are seeing right now, how your talk has implications for our current explorations in the direction of philosophy of science. So like say, for example, if the categories that we think when we're trying to understand the growth of science in the historical sense, the categories that we would think is of the worldviews of, the worldviews. Like say, for example, Kerala had a particular worldview, Chinese astronomers has a worldview,
yeah,
so on and so forth. Now, when we go from there to the contemporary understanding of science, where, like, say, as Vinita mentioned, and also as Aditya pointed out, people working in different pockets, local pockets of their own. So some of the categories that we have to look are not worldviews per se, because they are not completely idiosyncratic or, like, say, unique to themselves, but like say Lakatos has pointed about like the research programs and so on and so forth, like as Kuhn himself brings about like different research projects happening simultaneously, competing with each other, and
yeah,
some ideas the sociology of science brings in. Now, when we situate now ourselves in the contemporary science and try to understand how we can understand confluences, circulation, in the international science, not in the cosmopolitan sense, but in the internationalism sense, where everyone is collaborating, seeing what the other competing group are working with each other, how to outbeat the discovery of the other person or something like that.
yeah.
What are the categories that we have to use? If we can't use worldviews, then what are the analogous categories that we can use then?
Okay. You're actually asking a very difficult question, about, a kind of general categories we can use to understand, aside from worldviews, to understand the history of science. Because, different scientific, if you have chemistry, you have different kinds of theories that are there to explain chemical phenomena. Biologists have their own theories. Mathematicians have their own techniques, of mathematical techniques, and even, you can say mathematical theories. Now, what I am suggesting is I'm using the example of astronomy. This is a very particular case that I have studied, how it went into, Copernican astronomy. There were these three traditions that somehow came together, and the Copernican model somehow brought them together. And this led to modern science. Now, one can do the same thing with other areas. Now, mathematics is, of course, not a science, but one can look at how did the Arabs, for instance, bring great geometrical ideas and Indian algebraic ideas to come together. Omar Khayyam, for instance, developed techniques to do that, where you can say that he geometrized algebra. And other people have said that Descartes, brought these strange algebraic techniques, and, he algebraize geometry by giving, geometrical curves, algebraic equations. Now, one can then ask, but where did they, can we now look at Descartes' achievements as in some way combining, say, taking the Omakayam approach but inverting it, instead of geometrizing algebra, he algebraized geometry as he himself said, okay? But if this is the case, then don't we here have confluences of Indian algebra, Greek geometry, and something emerging that is new that later went into the making of calculus? What does this tell us about the history of science? Because what we tend to do now is to write the history of science in separate little tunnels. If you read, the history of the Cartesian achievements in mathematics, you kind of go back to the Greeks maybe, and not in the Greek direction. And then you go down, you have a European tunnel through which he gets connected. But he doesn't get connected to the other parts of the world from which we may have drawn ideas. This kind of history, but a lot of people have worked in separate pockets, for sure, And here I am thinking, especially over the last 30 or 40 years, when many scholars from many Asian countries have gone even to the West to study their own traditions, but from using the methodologies, historical methodologies, etc., that have been developed in the modern era. Okay. And they have developed pockets of knowledge, of the different contributions, the Arabic, the Chinese, the Indian, even the Japanese, and so on, because they come from certain cultures and they are interested in connecting the modern traditions with their own. What is really important, I think, for looking at the issue of science and the local is to bring these together. At the moment, as I think it was Vinita who said, do we have differences anymore? Okay, because we are all connected. I think if we keep emphasizing, that if we don't try to draw these different little pockets of knowledge that have been developed over the last 20 or 30 years and bring them together, then of course we will still write history the usual way. But I think that this will actually break down in the future, because within the West, it's very easy to write a history, a tunnel history from the West into the West. But I think if you come from other cultures like China or India or Middle East or Japan or others, most of the people who work on the history of ideas are actually looking not for comparative histories, not to compare, say, Indian mathematics with the Western or Chinese physics with the Western, but they are looking for connected histories. They're trying to connect, how did these? So these connected perspectives now are living in marginal pockets, let's put it that way, okay? And they somehow need to be brought together, But the dominant mainstream history and philosophy of science, as it is defined today, is still very much interested in comparative perspective, not connected ones. And yet a lot of people doing PhDs from outside the West are doing connected histories. And there's a vast reservoir out there, but it is existing in separated little pockets. How to bring it together is, of course, a very big issue. But conferences like what you are organizing, are a step, I think, in the right direction. But it needs to connect not just within India, but it needs to connect, with India and China and the Middle East somehow to make possible a history that can get out of these tunnels into what I would call a more global kind of history of science. And that's a very new direction. And I think it's an exciting direction, and I think the next generation of scholars, I anticipate, probably will take that direction more and more, because I see it happening in slow stages. Not when I was a student, but certainly now.
Yeah, thanks for pointing that out, Bala. I think Madhulika has a question to ask. Madhulika, can you unmute yourself? Yes, Madhulika, can you unmute yourself, or you want us? Madhulika, I can try now. We have.
I think I am now.
Yeah, we can hear you now.
Now? Yeah. Okay. Good evening, Professor Bala. That was amazing. And we've been following your work, and that's something that I use now in a course on politics of knowledge that I teach. I just wanted to add on to this last point. I had thought that I would just quietly listen to your lecture today. But, what I really did want to add to the last point that you were making is that the reason why comparative has been more important than connective is actually deeply political, isn't it? Because the whole point of history writing was to establish the superiority of a certain frame and paradigm of not just the science, but it was part of a larger imperialist project across the world. So it's not a coincidence that took precedence over every other kind of history writing. And today, if there are people talking about connective history, they are doing it you would know better than many of us how difficult it would have been to actually raise these issues and to find credibility in the argument that you're making in terms of saying that actually European science drew greatly from the knowledge systems of the three big Asian civilizations. So I think that that context of history writing, of academia, and the political context of academia, that's very important, isn't it? And I think that I'm really happy that a place like ICER is raising this. And I agree with you that it needs to go beyond this. But just the fact that they are raising it and set up a lecture series like this is, I think, a very worthwhile first step. Because within the social sciences, this churning has been happening for a while. But for a sciences institution to actually take this step forward is quite remarkable, don't you think?
Yeah, I agree with you. I think it is quite remarkable that a science institution, especially a science education and research institution, should want to take this up. And it also has a humanities and social sciences division within it that, it's supporting in this project. And and you are quite right to say that, the emphasis on the comparative versus the connective, it was part of the imperialist project. It was very important in the past to do these comparative studies in order to explain, why science, developed in the West. And you have that even in the social sciences.
Oh, yeah.
Okay. The Protestant ethic, is very closely linked to capitalism and development and so on. But now it becomes increasingly, then after the Protestant ethic, I remember that in the 90s, as Japan and other countries started developing, there was also the Confucian ethic that was seen as significant. And I remember attending a conference in Thailand where people were upset by the Confucian movement. And they said, no, it's got nothing to do with Confucian. It's Buddhist, because Japan and Hong Kong and all these other developing countries, populations that were largely Buddhist. Okay. Again, this is kind of, what I would call the Orientalization of the Max Weber thesis. And I think people have given up on that now. Okay. And the Weber thesis is no longer central to the social sciences. So I agree with you. But I think we are actually entering a different world where when I think about it, the big powers now are, of course, Europe and the US, but they are also Japan and China and India, and I'm sure soon, I'm not sure, somewhere in the Middle East or some other, in the Islamic world is of course very much divided, but if Turkey becomes something important,
yeah, exactly. I was thinking that.
Yeah, then you would get another kind of orientalization of the. This is, or the other alternative would be for them to combine together, to rewrite this kind of history with a more connective history. I don't know if you remember, in 2001 was declared by the United Nations to be the year of dialogue of civilization.
Absolutely. Yeah.
And I was teaching in Singapore at that time. And I was teaching the philosophy of science. And which is how, because here we have students who are Chinese, Indian, Malay, Islamic, and so on. And so, we thought, okay, let's look at the philosophy, history of science from this multicultural perspective. Because Southeast Asia is, of course, the meeting place of a lot of these cultures. The Indian influence was there, over a very, very long time. The Islamic influence was also there. And China is also, been an important factor here. So, and the course was actually received well by the students. But unfortunately, it went on a few years, but it didn't survive. But we did get funding to organize a few conferences and so on, like the ones being done now. So I agree with you. It is an imperialist project. But now that Western imperialism is in decline, I think, be accurate to say that. Maybe it opens the doors for other kinds of history writing. Yeah.
Absolutely.
And I agree with you. Yes. Thank you.
Thank you. Thank you.
Thank you, Madhulika, for that wonderful question. So anyone from the audience or the participants online who have questions? Can you share your question, observation? Are you able to unmute yourself, Ian?
Oh, good. Thank you. I needed permission to unmute. Thank you, Professor Bala. So I am very interested in the remarks relative to the essentialist versus situational in the sociology of knowledge side, because I've just come off of spending a week attending the Economist's World Ocean Summit, and I'm doing a lot of work in the thinking from an STS HPS point of view about aspirations to connect the local and the global with respect to idealizations of things like the blue economy, things like that. And if it's the case, and I'm not disputing from an intellectual point of view that Western imperialism is on decline, Western imperialism is on the ascendant from the point of view of the way in which the dominance of science is being framed as that which will lift up formally imperialized or colonized nations to a Western standard. And so I think there's a lot of thought that needs to be brought to bear on the cultures of knowledge, and particularly the way in which science from whatever tradition, natural sciences in particular, is integrated into local, let's say, governance and management plans, particularly when it comes to the deep connection between societal flourishing and ecological aspirations, right? Which is, you might say, what exactly high-flying notions like the blue economy as a kind of international concept, as a UN concept, or sustainable development, to take one of its cousins, is intended to articulate. That this is a balance between meeting the needs of local communities and yet harnessing the power, the universal power of scientific truth. They're really, I think, very important lessons to be learned from initiatives about the global and the local, from research projects like this, which could deeply inform these conversations that are happening at levels like the UN or whatever. So that's really an observation, not so much a question, but happy to hear people's thoughts on that.
Yes, I tend to agree with you, that the idea of science as lifting all societies up to Western knowledge, by Western knowledge meaning the knowledge of modern science, and that science is defining the way, how we go about setting about ways of governance and so on, is in some sense could be negative, because it doesn't seem to gel with certain environmental concerns. Okay. Now, the way I can answer that question is, I think, looking at philosophy of science from this different angle of other cultures can also help deal with the problem you are addressing. I don't want to bring this up, but I actually wrote another book, Complementarity Beyond Physics, Niels Bohr's Parallels. Okay. I don't want to bring that book up, but it's directly relevant to what you just said, because Niels Bohr had said that in order to understand some of the issues that crop up in quantum mechanics, you need to turn to thinkers like Lao Tzu and Buddha, okay? I use that as an excuse to say you need to turn to the Chinese and Indian pre-modern philosophical traditions. And Niels Bohr also said that complementarity, has very important implications for understanding not just physics, but there's a psychological complementarity, biological complementarity, and even what he called anthropological complementarity. And a lot of these issues, and a lot of environmentalists have also appealed to quantum mechanics. So in that book, it actually suggests that the break that quantum mechanics brings about in the way we understand the philosophy of nature, actually also requires us to go back to philosophical traditions, certain so-called pre-modern, but they could also be postmodern Asian, philosophical traditions. Okay. Now the reason is actually quite simple, because modern science was built on the image of machines, of mechanical systems. And somehow this science that has been built on this image is now posing a great threat to biological systems, living systems, and also to sentient systems like animals and so on. Okay, animal rights and all tie in with this. And the worldview and these kinds of organic worldviews or animist or agentic worldviews, which modern science repudiated, is precisely the kind of worldviews of pre-modern cultures. Aristotle's worldview was organic. The Chinese had an organic materialist worldview. The Buddhist idea of dependent origination is very much kind of an organic perspective, okay? And which makes them in certain ways more compatible with quantum mechanics. I mean, this is what I argue in the book, you know, and I think there is something to that. So when we actually redo the history of science in a connective perspective, we also allow new connections to be made, not just about understanding science in the past, you know, the science we have constructed in the modern era, but also understanding how we can go forward by drawing on other parts of earlier traditions to construct a more ecologically sensitive science. But doing this is, you know, it's going to be a very difficult task, as difficult as the construction of modern science. But at least you need to start a dialogue before you can move in that direction. But thank you for your question. Yes, it makes, you know, I agree with you.
Thank you, Ian, for that observation. And if there are no other questions, I think it's time to, call it a day. And thanks, Bala, for spending your time. And we are aware that like it must be like close to 11 o'clock in Singapore right now.
Yes, it is. It is 11 right now at night. But it's not past my bedtime, so don't worry.
But yeah, thanks for spending your time post your dinner with us.
And thank you very much, Arun, for inviting me and for participating in this great session. Thank you.
Yeah, it's our pleasure. And thanks everyone for spending the time here, taking time and spending. And we'll meet again on Thursday at soon. And good night. Thank you, everyone.